So we are in the last phase of designing our reliable data transfer protocol. Let me remind you that this lecture is in continuation of two previous lectures on the principles of reliable data transfer protocol. So those students who have not gone through those previous two lectures would find it difficult to understand the context of this particular lecture. So if you have not gone through those two previous lectures, I urge you to complete them before attending this particular lecture. Let's quickly summarize what problems were solved by the second version of the Reliable Data Transfer Protocol. Let's briefly summarize what problems were solved by our Reliable Data Transfer Protocol version 2. In the version 2, we assumed that the underlying layer, the network layer, could introduce a corruption, the error during transmission. So if corruption of packets happened during data transmission, the receiver side would receive a corrupt packet. So our main task was how to detect corruption of packet. This was done by using checksumming. Now, what would do when a corrupt packet would be received? It would send an acknowledgement to the sender saying that I have received a corrupt packet, and if such an acknowledgement arrives, then the sender would retransmit that particular packet. So basically, three important steps. One step is detection of corruption by the receiver, then acknowledging or informing the sender about that corruption, and then retransmission of that packet by the sender if such a corruption of data took place and acknowledged by the receiver. Version 2 also handled the issue of duplicate packets. If an acknowledgement itself was corrupted, then due to the retransmission of packets, it would be difficult for the receiver side to distinguish between new packets and old packets, and to solve those problems, a new concept of sequence numbers was used. So today we'll see our final version of our reliable data transfer protocol. Today we'll introduce the final assumptions. This final assumption would actually reflect how our actual network layer works. Today we'll introduce the loss of packet also. So along with bit level errors, we'll also introduce loss of packet. That means while transmission of the data packets, those packets can get lost also. So what changes would have to be incorporated in our protocol to handle the loss of packets? This we'll see today. Just a quick view of our rdt 2.2 protocol of the sender side. This was clearly explained in the last lecture. So again, I urge you to go through that lecture once again if you have forgotten about the rdt version 2. So this was the finite state machine of the sender side. All those concepts that were introduced, acknowledgement, retransmissions, all those different states, and also this is the receiver side. Receiver side again, creating acknowledgement and informing the sender about corrupt packets, using checksumming to detect corrupt packets, all those issues that were solved by our reliable data transfer protocol version 2. And also, before introducing this concept of packet loss in our protocol design, just to have a very brief understanding that we talk about packet loss, but where does actually this packet loss happen, or why does this packet loss happen during data transmission? If you remember our discussions about the basics of networking, I guess you have certain idea about losing packets in our intermediate switches or routers. Remember, there is something called queuing or something called buffering in our intermediate routers. Now, if there is a high traffic, heavy traffic, during that time, the buffers in the intermediate routers can overflow, and this overflow may result in loss of packet. This is one of the very major reasons why packet loss takes place during data transmission. Packet loss can also happen due to problems with network hardware. For example, for instance, suddenly if an intermediate router goes down during data transmission, then packet loss would obviously occur. Power failure in those intermediate routers, due to power failure also packet loss can take place, because power failure will actually cause the intermediate routers to go down. Software bugs actually can also cause packet loss. For example, say though it's very rare, it can happen that due to a software bug, a routing table was mismanaged. The routing table was not created correctly, and this would cause a packet to be sent to a different destination. and the actual destination will actually it can be a case of packet loss for the actual destination because it did not receive the packet for due to the bug of the software. Packet loss can happen in Wi-Fi and cellular networks because of the nature, because of the characteristics of such cellular networks, because data travel by air, and because of cases of interference. Packet loss is a notable characteristics of Wi-Fi networks. This we'll separately discuss when we come to cellular networks. Another reason of packet loss is due to cyber attacks. People can actually create attacks to make such sort of things of losing packets or destroying packets during data transmission. Now let's get down to our actual design of our reliable data transfer protocol. Now this was the assumption of version 2. So in the version 2 we assume that the network layer does not lose packets but bit level errors can take place. Now in the final assumptions we introduce the concept of losing packet also. So here we introduce the saying that the network layer lose packets as well as having bit level errors. So both of these can take place, errors as well as losing of packets, and whatever changes we will do in the protocol, this we will call rdt version 3. Again, this would be the final version of our protocol. Now remember the original task. What was the original task? The original task was that how reliability can be maintained while working over an unreliable medium. Because network layer is unreliable, what is the unreliability here? The unreliability is the fact that it can lose packets. The unreliability is in the fact that errors can happen during transmission. So network layer is unreliable. But our transport layer TCP has given a guarantee to the application layer that the data will be delivered. Data will be correctly delivered no matter what the network layer does. So because network layer is unreliable, so it has to provide the guarantee of delivering packets, provide the reliability factor. That's why it has to perform certain actions. Some of the actions we've already seen, actions like acknowledgement, retransmission, all those factors we have already incorporated in version 2. Now today we'll see how this loss of packets will be handled by our protocol. So what could be the major issues when packet loss takes place? So there will be two questions, two basic questions which has to be handled if packet loss happens. The first question is how to detect packet loss. How to detect packet loss. And the second question would be what to do if packet loss occurs. So these two things are to be handled by a protocol. How to detect a packet loss, how to detect errors. We have already seen errors was detected using checksum. Today we'll see how to detect packet loss and what to do if such a packet loss occurs. I guess you should be able to answer the second part of the question. What to do if packet loss occurs? Before answering the first question, let's handle the second part. What to do if packet loss occurs? From the concept of rdt version 2, you should be able to easily give an answer. There is only one single way, and that way is retransmission of packets. So retransmission of packet. Just like we retransmitted a packet when error took place, if error took place, it retransmitted the packet. Same way, if a packet loss happens, again do retransmission. But this would introduce again the problem of duplicate packets. So if there is a retransmission of packets, duplicate packets may be transmitted. How? We'll see. But how to handle duplicate packets? Again, that has been already been solved using the concept of sequence numbers. So the second part, what to do if a packet loss occurs? The simple answer is the sender retransmit those packets which got lost. Now we'll see the first part, how to detect packet loss. Now remember, packet loss happens in the network. Now there are two parts, the sender and the receiver. The sender is sending data, the receiver is receiving data. The packet loss happens in the network. That means someone, either the sender or the receiver, has to detect the packet loss. Someone should understand that packet loss occurs. Now who will detect? Remember, in case of errors, it was the duty of the receiver to detect errors. There was a role of the sender also. Sender calculated this checksum and inserted in the packet. The receiver recalculated this checksum, and if it found that there is certain mismatch about the checksum, then it understood that errors have taken place. So it was the role of the receiver to detect errors in packets. But who will be responsible to detect packet loss? Remember, again, packet loss is happening in the network. Nobody, neither the sender nor the receiver, would actually know what is happening. Because a packet loss may happen in the intermediate router, and that intermediate router has no role in informing. Intermediate routers will never inform either the sender or the receiver that a packet loss has occurred, that I have dropped packets. These sort of things it won't do. So if the intermediate routers where packet loss happens would not inform either the sender or the receiver, how would the sender and receiver know that packet loss has taken place? Now, the important fact in networking is that in networking, the task of detecting packet loss is work of the sender. This is a very important concept. The sender is responsible to detect whether a packet loss has taken place or not. It's a role of the sender to find out whether a packet has got lost. Now, how will it do it? How will the sender detect whether a packet has got lost? Will it ask the intermediate routers? Remember, the intermediate routers won't respond. The sender cannot ask the intermediate routers whether you have dropped my packets. It won't respond. So how it would know that a packet loss had occurred? Can you think for a moment and answer this question? If you have gone through the version 2, again, you can come up with an answer. Now remember what happened in the version 2. A sender sends a packets. The packet arrives at the destination. The destination sends an acknowledgement. Then the sender can send the subsequent packet. It waits for an acknowledgement. The acknowledgement comes. It can send the next packet. If a acknowledgement comes saying that an error has occurred, it would retransmit the packet. And when an acknowledgement, a correct acknowledgement arrives saying that the packet has been received correctly, then it would go on transmitting the subsequent packet. That means there is a cycle. Send, wait for acknowledgement. If a positive acknowledgement comes, send the next packet. If an acknowledgement comes saying that error has taken place, then resend the packet. But again, wait for an acknowledgement. Correct acknowledgement arrives saying that the packet has been received correctly, send a subsequent packet. So basically it's a cycle. Send, wait for acknowledgement, send, wait for acknowledgement, send, wait for acknowledgement. And this answers your questions. If a packet got lost, that means that packet never arrived in the destination. It never arrived in the destination means it won't send any acknowledgement. Whether it is received correctly or incorrectly, that particular question will arise only when the packet arrives. Now, if the packet does not arrive, if the packet got lost, then obviously the destination would never send an acknowledgement. So, if the sender does not receive an acknowledgement up to a certain amount of time, what the time is, we'll see. That's a different discussion. But let's now assume that if the sender does not receive an acknowledgement up to a particular amount of time, then it can assume that the packet has got lost in between. It may actually not happen. It may happen that the packet has not got lost, but it is suffering an unordinate delay. This may happen. This part we'll see. But safely assume that, as of now, safely assume that if an acknowledgement is not coming to the sender up till a particular duration, what duration can be, we'll see just now. But if it is not receiving an acknowledgement, then it can understand that a packet has not arrived at a destination, and that's why no acknowledgement is coming. So the first question, how the sender detect packet loss? it can detect by only one way, and only one way is there. The only one way is that it is not receiving an acknowledgement from the destination, from the receiver, because no acknowledgement is coming from the destination part. That's why it assumes that a packet loss has taken place. And when it understands that packet loss has occurred, when it detects a packet loss using this method, what is this method? Say it starts a timer of a particular time, and if an acknowledgement is not arriving within that particular time, it retransmit the packets. So the first question, how does packet loss is detected? This is detected if an acknowledgement is not coming to the sender after a particular duration of time. Now the question is, what would be the duration of time? How long should the sender wait until and unless it understands that an acknowledgement is not coming? That's why I should now retransmit the packet. So can you say how long should the sender wait? How long the sender should wait to assume that packet loss has taken place? Go back to your discussions of the fundamentals of networking, those delays. Now remember, a particular time is required for a packet to go from the sender to the destination. Those times, if you remember, all those delays, propagation delay, transmission delay, queuing delay, all these delays added up. I guess you remember. So we have already calculated how to calculate this delay, how long it will take for a packet to go from one end to another. So there's a particular time taken for a packet to go from the sender to the destination. And again, an acknowledgement is coming from the destination to the sender. So a complete round trip time. A packet going from a source to destination, and then an acknowledgement of that particular packet coming from the destination to the source. So this total round trip time of a packet going from source to destination and an acknowledgement coming from the destination to the source. Now if I can calculate this time, we already know how to calculate this time. So if an acknowledgement is not coming with for a duration similar to the round trip time, then obviously I can understand that packet loss has taken place. I already know how much it that what time is how much time is taken for a packet to go from the source to the destination, and I also know how much time it takes for an acknowledgement to come from the destination to the source, and say it is 40 millisecond. Say total 40 millisecond is taken for a packet to go from source to destination, and then an acknowledgement coming from the destination to the source. Now if an acknowledgement does not arrive by 40 milliseconds, or say slightly more extra time is added to account for other things, so say 50 milliseconds. So if a acknowledgement is not coming within 50 milliseconds, whereas the round trip time was 40 milliseconds, then the sender can assume that packet loss has taken place. How? Because it has not received an acknowledgement. If the packet has been received at the other, then it would have got an acknowledgement within that stipulated time. But because it did not receive an acknowledgement within that stipulated time, now it can assume that the packet has got lost. And once it understands that the packet has got lost, it can retransmit the packet. So if I know that my round trip time is 40 millisecond, I can set my timer to 40 millisecond, or say 45 millisecond, or say 50 millisecond. And if the timer times out, if that I put the timer as 50 millisecond and the timed out after 50 millisecond and I did not receive an acknowledgement, then I can, as a sender, I retransmit that particular packet, because I have clearly understood that a packet loss has taken place and I did not receive an acknowledgement, so I am now retransmitting my packet. So the main question has been answered: how to detect packet loss, and what to do if such a packet loss occurs, what to do retransmission, how to detect if I do not receive an acknowledgement within a particular time. Basically it's a round trip time plus some duration. If I do not receive an acknowledgement within that particular time, I retransmit the packet. Now this will introduce something new also. Say my round trip time is 40 milliseconds and I have set my timer to 50 milliseconds. It may happen in networking that some packet suffers a huge delay. It may happen due to certain conditions in the network. A long delay may happen for certain packets. Now assume that there was some network traffic, huge traffic, and that's why a packet got delayed during transmission. Now I have set my timer to 50 milliseconds. Because of the huge delay, say the packet arrived at the other end, say after around 50 milliseconds. Now the acknowledgement is coming. Say for the acknowledgement to come, another 20 millisecond is there. That means the whole round trip time now it took is 70 millisecond. But my timer itself went out at 50 millisecond. I hope you are understanding it. That means I have set my timer at 50 milliseconds. But because of an network traffic, the packet arrived at the destination after 50 milliseconds. Now the acknowledgement is coming. Say it is taking under 20 milliseconds. That means after 70 milliseconds, I have received an acknowledgement of the packet which I sent. But my timer has already went out at 50 milliseconds. And because I did not receive an acknowledgement within 50 milliseconds, I have retransmitted my packet. But the original packet did not get lost. The packet actually arrived at the other end. But it arrived late. And because it arrived late, my timer has got out and I have now retransmitted the same packet. That means a duplicate packet is gone. The original packet did not get lost, but the timer got out because there was a delay. And because my timer went out, I have now retransmitted packet. But will it pose any problem? No, it will not pose any problem. Retransmission of this packet, this duplicate packet, will not pose any problem. If you have any doubt, please go back to the second lecture of RDT version 2. This case of duplicate packet has been solved using the concept of sequence numbers. Because we use sequence numbers, if I send duplicate packets, how many times I send duplicate packets, it will not cause any problem. If a receiver receives 10 duplicate packets, 10 packets of the same sequence number, it can simply discard those duplicate packets. So if I send a packet and is received at the other end after much delay, and because of the delay my timer goes out, if I retransmit the packet, so a duplicate packet arrives at the destination, just by looking at the sequence number it understands that it's a duplicate packet and it will simply discard the duplicate packet. So the first problem of duplicate packet is solved by using sequence numbers. Now there is another problem. The other problem is that the acknowledgement can got lost. The sender sent a packet to the destination. The destination correctly received the packet. It sent an acknowledgement, but the acknowledgement got lost. So if the acknowledgement got lost, after that timer is over, the timeout occurs, and the sender did not receive an acknowledgement because the acknowledgement got lost. So what it will do? It will again retransmit. Now remember, the packet was correctly delivered. Say it was delivered at the correct time. It's the destination sent an acknowledgement, but the acknowledgement got lost. And because the acknowledgement got lost, after some time the timer went out. Now the sender retransmitted packet because it did not receive the acknowledgement. The same problem and the same solution. It sent a duplicate packet. That receiver received a duplicate packet, but it has been already solved using the concept of sequence numbers. So both of my problems are solved. What are those two problems? The first problem is inordinate delays. If inordinate delay happened to packet and the packet was delivered and it timed out, then it would retransmit a packet, a duplicate packet. And the second problem was receiving loss of acknowledgement. Due to loss of acknowledgement, the timer goes out, and again there is a retransmission of duplicate packet. But again, this problem is solved using the concept of sequence numbers. So both of my problems are solved. So now I can actually go to my protocol. So what to do with my protocol? So first let's see the sender side. The sender side. So what would be there in my RDT version 3? So in my version 3 there will be a simple addition. So apart from all the things in rdt 2.2, all those things that were there in RDT2, they would be already there. This would be obviously be there because it has to handle the bit level errors. But apart from all those things, there is only one single step. The single step is when a packet is sent, start a timer. And what would be the time? The time is basically the RDT plus certain amount of time. we'll later on see how to actually calculate the time. We already know how to calculate delays, and what would be the actual time of this timer we'll see in a subsequent lecture. But again, when a packet is sent, start a timer. If the timer goes out, simply retransmit the packet. And if an acknowledgement arrives within that the timer goes out, then simply stop the timer. So there should be some way of starting a timer, stopping a timer. So every time a packet is transmitted or retransmitted, the timer is started. If an acknowledgement arrives before the timer goes out, simply stop the timer. If the timer goes out, then retransmit the packet and again start the timer. So basically we have added this step of adding a timer. If it times out, retransmit the packet. As simple as that. This simple addition of this simple step completes our sender side of rdt 3.0. So this is our final protocol, rdt 3. So rdt 3 will solve all the problems of the unreliability of a network layer. So all those unreliability, losing of packets, bit level errors, these are handled by using a reliable data transfer protocol like this. So basically what are those ways of solving the unreliability? The ways of solving are detecting errors, detecting packet loss, and retransmission of the packets. So the basic question of how does TCP give guarantee to the application of delivering data when the underlying layer is unreliable? This question is often asked in interviews. How does transport layer give guarantee of reliable delivery of data when the underlying layer itself is unreliable? The simple answer is by means of retransmission and acknowledgement. By means of acknowledging data, by means of retransmission, by means of timer, by means of timeout, by means of retransmission, this reliability is guaranteed. That means by means of retransmission, somehow at some point of time a packet will be delivered to the destination. So this is our solution for rdt 3. This is our final protocol. So apart from all the things of rdt 2.2, the new concept of timer is added. What about the receiver side? Receiver side need not do anything extra. If you think of it, receiver side did not do anything from rdt 2.2. Whatever it did in rdt 2.2, it will continue to do the same thing. The timer has been added to the sender side only. Remember, the receiver has no role in detecting packet loss. So there is no change in the receiver side. So the receiver side of the rdt 2.2 is same as the receiver side of rdt 3.0. Only change will be in our sender side. And what will be the change? The change is addition of a timer. And this gives our final protocol, the final design of our reliable data transfer protocol. And if we have understood this, you have understood a lot of things about TCP. This is actually how TCP ensures reliability. Obviously, this is not TCP. TCP incorporates some more other things, but this is the way of ensuring reliability. The major task of retransmission, acknowledgement, these are the main part how reliability is ensured by TCP. So this protocol, which we call as reliable data transfer protocol, this mechanism of acknowledgement and retransmission is inherently built in TCP. So if you have understood this, you have understood the main task of TCP, how to ensure reliability. And this is the finite state machine of the sender side of rdt 3.0. If you look at it, you see here. So when it sends a packet, it starts a timer. So every time it sends a packet, it starts a timer. And if there is a timeout, come to this state. If there is a timeout, it again sends this packet and then restart the timer. So this is the extra step. The rest of the steps are same as rdt 2.2. The other steps which we have already seen in rdt 2.2. The receiver side has no change. So I need not show you the receiver side because the receiver of rdt 3.0 is same as the receiver side of rdt 2.2. So this is our final design. So with this in mind, we'll now in the subsequent lecture we'll go to the actual work of TCP. What other things TCP incorporates in itself. So again, please consult your textbook to go for all these states of your rdt 3.0. We have already discussed, but again, please consult your book and see all the states, what they are doing, how it is going from one state to another, all these different states. And now, since we have designed our protocol, let's run our protocol. Let's see our protocol, our final protocol rdt 3.0 in action. First case, a correct operation, a operation with no loss. No loss of data has taken place. What will happen? This is the sender side, this is the receiver side. Remember, we are using the sequence numbers, and remember, if you have studied the rdt 2.2, we require two sequence numbers 0 and 1. Only two sequence number is enough to distinguish between different packets. So the sender sends the first packet, the receiver receives the packet, it sends an acknowledgement. This sender sends the subsequent packet, it sends an acknowledgement, it receives an acknowledgement, it sends the next packet. So this goes on and on. So this is the normal operation. Now let's see if a packet is lost. So the sender sends a packet number 0. The receiver receives packet number 0, sends an acknowledgement for packet number 0. The sender receives the acknowledgement for packet number 0. It sends the next packet with sequence number 1. Now this packet got lost in between. The timer is running. The timer goes out. It did not receive any acknowledgement within that timer. So it resends packet 1. So this packet 1 is resent. Now this packet arrived correctly. The destination sent an acknowledgement for this packet, acknowledgement of packet number 1. It receives an acknowledgement. Then it can send a subsequent packet, which would have a sequence number 0. So I guess this should be easy to understand if you have understood the design. Now let's see another case. Loss of acknowledgement. Remember, packet can got lost. Packet can got lost in between. This we have already seen. So first packet sent, packet receive, acknowledgement sent. It receives the acknowledgement. It sends the next packet with sequence number 1. It correctly received the packet. It sends the acknowledgement for packet number 1. Now this acknowledgement got lost. This particular acknowledgement got lost. The timer goes out. So it resends packet 1. The packet was a resend. Now remember, this packet was received correctly. This packet was received correctly because the packet was not lost, the acknowledgement was lost. So it resends the packet 1, it receives packet 1. Now it has detected a duplicate. Because it has already received packet 1, now it has received a duplicate. It sees that the sequence number is same. It can now simply discard it. So what it will do now, it sends an acknowledgement for that packet again. Because it have understood that the acknowledgement was got lost, that's why it has received a duplicate packet. So it again sends an acknowledgement for packet 1. Now it can simply delete this duplicate packet, but it sends an acknowledgement for packet 1. The sender receives the acknowledgement for packet 1, and then it now sends the subsequent packet. As simple as that. And then if there is a premature timeout. What is premature timeout? Premature timeout is when there is a delay in receiving of a packet. So let's see. The sender sends packet 0. The receiver receives packet 0. It has received correctly. So it sends an acknowledgement. It sends the next packet 1. Now assume that there is a huge delay. Say this timer is of 40 milliseconds. The timer is of 40 milliseconds, but it has received this packet say after it has received after 34 milliseconds, and it will send an acknowledgement. Till the acknowledgement arrives, some more time takes place, say plus some amount of time, say another 20 milliseconds, so total 54 milliseconds. So this acknowledgement arrives after 54 milliseconds, but the timer itself went out at 40 milliseconds. So after 40 milliseconds, it returns me that packet, assuming that the packet has got lost. So again, it receives a duplicate packet. Which duplicate packet? That packet 1. It has received a duplicate packet. It was delayed, but it received a packet. But again, no problem. It has received a duplicate packet. It can simply delete this duplicate packet. It again sends an acknowledgement for this packet. And then this packet which was delayed, its acknowledgement has arrived in between. Remember, it was correctly received there. So after 54 milliseconds, the acknowledgement of the original packet that was originally delivered has arrived. So at this moment itself, it can send the subsequent packet because it has received an acknowledgement. What about the duplicate packet acknowledgement? It has arrived. That acknowledgement of the duplicate packet has also arrived, but it doesn't matter because it has already received that acknowledgement. It has transmitted the subsequent packet, and it will send the next packet when only it receives the acknowledgement of this packet of sequence number 0. So I guess you have understood all the situations of our RDT protocol 3.0. So this finishes our design of our reliable data transfer protocol. So that's it. We have seen how TCP ensures reliability while working over an unreliable medium. We have seen how a reliable data transfer protocol works by means of acknowledgement, retransmission. So we have understood the core functioning of a reliable data transfer protocol. Next lecture, we'll start with some of the implementations of TCPs, different flavors of TCP like go back and selective repeat. Till then, you also refer to your textbooks and see all the other different aspects of this reliable data transfer protocol. Thank you.